Hello, it's Keith here, and this is lesson 57 of the platform-specific series of my 65 Virtual Assembly programming tutorials. We're looking at Mintile, my software tilemap routine, and we're looking at it on the Apple II today. You can see it just here, if we just fire this up. And the example we've got here has two simulated sprites moving around the screen. There's the top one here, which is controlled by me, and the bottom one, which is just computer controlled, just to show we can have multiple objects on the screen. And if I press the fire button, if I remember what it is, this will horizontally flip the sprite, and it will scroll the background horizontally as well, just to show that the tilemap can be scrolled and just to show that we have horizontal flipping functionality. Now, this version of the code, Mintile, can only horizontally flip, it can't vertically flip. The reason for that is that's something that I'm going to do in a later, more advanced tilemap routine. This Mintile routine was originally written for a Z80 based game, which was it was a game called Chibi Fighter, Street Fighter parody, and to make that game I needed the characters to be able to turn around, but I didn't need them to flip upside down. So I created the functionality I needed for that game, but no more, because my plan was always to port this to as many systems as possible, and adding extra functionality means a lot more work and code, and so at this point it wasn't viable, or it didn't make sense. So what we've got today is a minimal tilemap example. It shows a scrolling tilemap image, and we're going to look at the code now. What we're going to look at is the parts of the code that are related to the tile drawing. We're not going to look at the parts, things like reading the joystick, moving objects mathematically around the screen, because that's been covered in the simple series before. We're just going to look at the drawing routines that have been written for this. The vast majority of Mintile's code is multi-platform, so if you want to see the Mintile series, there's a whole tutorial series covering the actual multi-platform code, which runs in the same way on all of these systems. It's just the platform specific module we'll look at today. Now, on this system, the memory address of the screen base is 4000. Now, the screen is actually larger than we need it to be, so we are working on a screen of 32 tiles by 24 tiles, which is 256 by 192 on most systems. Because on this system, because of the strange way the Apple II screen works, the tiles are actually 7 pixels by 8 pixels, so that's a single byte, 8 lines tall. A little bit odd, but that's the way this system works. So we're centering that to give our virtual screen a central position. Now, when we're drawing the entire tilemap, we start from this screen-based position, but when we're drawing the little sprites, we need to calculate the exact location that we want to draw in VRAM. And to do that, we have the get screen pos routine. Now, this is a slightly tweaked version of the one I've used in the past. The mathematics are basically the same. The only thing is that this one has been converted to work in logical units. It's also been coded to work in entire vertical tiles, so we can't move half a tile down. That was a luxury we could not really afford on this system because of the weird screen memory layout. Moving half a tile is much more difficult than moving in full 8 pixel tall jumps, and so to simplify the code and allow some maintained speed, I am limiting as to entire tile vertical movements for the sprites. So you can see they jump around quite a bit. If you just see when this one moves, you can see it's moving in entire tiles there. It's a compromise to allow the speed, and so we're taking the Y position here, and we're effectively converting to a number of tiles here. The X and Y coordinates are in logical units. One logical unit is 2 pixels in my tutorials. I'm using this on all of my tutorials now. It's far more convenient, and on 8-bit systems, per pixel horizontal movement is often impossible or too expensive processor-wise. And vertical movement, it's not a significant compromise, and it allows us to have a 256 1 byte coordinate for our X and Y position, even if we need off-screen areas. So it's far more convenient. Okay, so there we are dealing with the Y coordinate, but basically the problem is that you may remember the screen is actually split into 3 different sections. The Y line number, if you took the bits of the line number here, they are basically split into 3 sections, and we have to do a completely different calculations for each of those sections. Now, the benefit to us is that when we want to move down a line, basically we need to just add 4 to the high byte of the VRAM destination. But the problem is that we've got basically 3 sections of the screen, and we need to effectively multiply the section number by 28. Now, the way I do it in my tutorials is that I actually basically mask those 2 bits, and I use those 2 bits, and then I do an add here based on those the value of those bits. So it's not really a multiply, it's a branched calculation there. And as I say, that's why it would be too complex to allow a tile to be halfway between those boundaries, because we'd have to do these kind of calculations every single line. When we do the next line, we'd have to check if we'd gone over a boundary, so that's not going to be really possible. Here we're taking the x coordinate, we're effectively dividing by 4 because there's 4 logical units per tile, and then what we're doing here is we're just adding 4 to the VRAM destination, the HL pair there, and that is because we're centering the virtual screen, as I say, 32 tiles wide, 24 tiles tall, 256 by 192 on most systems. Now, when it comes to drawing graphics to the screen, be it the entire screen or just a little sprite, we're actually working with a tilemap, even the sprites are a miniature tilemap, and the way the multi-platform code works is it breaks the tilemap up into individual strips. So our sprite would be a series of strips, and what it does is it will send the draw command to the platform specific code, and that will draw starting from the left going to the right, and it runs that repeatedly to draw the larger object, be it the screen or the sprite. So here's the code that's going to do that. Now throughout this code, the X register contains 0, so we'll use that in various places. What we're doing first here from the 0 page pair BCS, that's a 16-bit pair, is we're loading in the tile number we want to show. Now a 0 value here has a special purpose. In the background, it's actually, the background tilemap is actually a cache of changes, and so a 0 there means no change, leave it unchanged, and that's because the code doesn't use a double buffer, which is why you can see some flickering there. That's simply because of most systems, a lot of 8-bit systems struggle with the extra memory requirements of 2 screen buffers, and so having that as a hard limitation for this example I thought made it more portable. And so we have that function where basically a 0 is an unchanged entry that won't be drawn. If we've not got a 0, we're checking tile clear. If that is not 0, we're actually going to clear the tile back to 0. We would do that for the cache of the background, but not for the sprites. If we zeroed the sprites, we wouldn't know what to draw next time. So that's why we're not doing that there. Now what we're doing next is we're taking the tile number that we want to draw and we're effectively multiplying it by 8. That's because there's 8 lines per tile pattern. And so what we're doing here is we're calculating the offset within the pattern data that we want to show. Now the DES pair here, DS and ES as a 16-bit pair, is the source pattern data. If we just have a look in our code here, we should see that somewhere. Here it is. So here is the sprite data for this system. These are the patterns that are being used to draw the tiles to the screen. So those are what we're going to be drawing, and here we've calculated the source address for the pattern data in HLS. That's what all of this has done. Now in the next part of the code, basically we're going to use Y as the offset in the source data, and the HL pair is the VRAM destination. So here we're loading a byte from the source pattern and then we're writing it to the screen. We're then incrementing the H part of the HL VRAM destination 4 times, effectively adding the 400 that we have to add for each of the lines within an 8 pixel tall strip. And that's why, as I say, it's far more efficient for us to always assume we will be limited to an 8 pixel vertical movement here. So that's moving us down one line. We're then incrementing Y and seeing if Y has reached 8, which would be the last line of our pattern. We repeat until it has. So that is drawing the 8 lines of the pattern. Once we've drawn the pattern, we're incrementing the BCS pair in the 0 page. That is the tilemap source. So we're moving to the next tile. We're incrementing HL, moving across one screen to the next tile position. And then we're decreasing the tile count. Now this is the width of the strip that we're currently drawing, and we repeat until we've done. So that's how we draw our unflipped tile patterns. What about the flipped ones? Well, we need to have flipped data, obviously speaking. Now there's a couple of ways we could do that. We could have a second set of all of our pattern data. It's going to take a lot of memory. Or we could calculate in real time when we want to draw a pattern and flip the data. That's going to be slow, but there is a compromise. We can create a lookup table, pre-calculate all 256 flipped possible bytes to their X flipped equivalent, and then read in from that lookup table to do the job. Only uses 256 bytes, so unless we've got very few patterns, that's going to save memory, and it's going to be far, far faster than doing the option of flipping in real time, which would be very slow. So that's what we're going to do. So here we're loading the address of the lookup table. The lookup table must be byte aligned so that the bottom byte of the 16-bit address starts at 00 and goes all the way up to 255 because we need that to be the byte we want to convert. So we're loading the address of the lookup table into HL here, and the offset is in Y. Now, because of the way this table is going to work, the offset is also the source byte we want to convert. So we're transferring Y to A here, and then we're effectively shifting the bits. Now, a byte on the Apple II, the first bit is the color attribute, so that will define which of the two possible colors this block will actually use, and so we're not flipping that. We want that to stay the same. But the other 7 pixel data values, we're shifting out of the right of the accumulator and back into the left in our destination C here. So we're basically flipping all of the bits, and then we're storing the result into our lookup table. We increment Y until it goes over 255 back to 0, and at that point we've finished, and so once we've finished we return. So that's how we're flipping our data in our lookup table. Well, how do we use it? Well, the multi-platform code will actually call a different version of the draw strip routine for the horizontally flipped data. Now, the drawing actually still occurs from left to right. It walks backwards through the source tilemap and flips the bitmap pattern data instead. So that's how we're doing it. Now, the BC pair in the 0 page will point to the lookup table. The B part is being loaded with the top byte of the lookup table address here. And then what we're doing is the same as before, loading in our tile number, zeroing it if required, calculating the offset to the pattern data, and that's being done there. And the pattern data is, of course, the same pattern data as last time, unflipped. The flipping is being done in real time. So that's what we're going to do here. So once again, the Y register is going to be the offset to the source pattern data. So we're loading in a byte unflipped from our source pattern data here, and then we're loading that value into the C part of the BC pair in the 0 page. Now the B part is pointing to the lookup table. So BC is now an entry in the lookup table, and because of the way we define that lookup table, the byte we read back in the next line is the flipped equivalent of the value in the C entry in the 0 page. So that is loaded in the flipped byte that we want to write to the screen. So that is XFlip the data. So that's all we do. The lookup table has basically meant that we only need 2 extra commands here to actually flip the data rather than a ton of bit shifts. So it's far, far faster. And then we're just doing the same as before, moving down a line, repeating for 8 lines. We're walking from right to left backwards through our source tilemap this time, and we're going from left to right still in our VRAM destination, so that's just all the same. So that lookup table is really making things very easy for us, and that's certainly what I would recommend you do for this kind of flipping. Now, this version of the code only does XFlip, it doesn't do YFlip, but I am working on a successor to Mintile known as MaxTile. Not very inventive naming, I know, but that will add more functionality. It will support XFlip, YFlip, X plus YFlip. It supports pseudo transparency where parts of the tile are not drawn if the byte's 0 basically, and it also supports fast filling and things. There's a few tricks it's got to allow for faster drawing of large areas, so that's something that's coming as well. Anyway, go to the website and download the example here. Hopefully you can find something interesting or useful in it, and as I always say, you're welcome to take it apart and use any parts of it you can in your own project, even if they're commercial. Thanks for watching, and goodbye.